In this video, I'm going to talk about nucleophilic addition reactions on aldehydes and ketones. So when you look at the structure of a ketone or an aldehyde, the electrophilicity of the carbonyl group derives from two effects. One is the resonance effect, and the other is due to inductive effect. The carbonyl carbon is polar in nature, so you can redraw this in this structure where oxygen has a slight negative charge, this has a positive charge, as a result of which nucleophiles can attack at this carbon center, which is electrophilic in nature, and you can see that when the nucleophile attacks this electrophilic center, which is carbon, it forms a tetrahedral intermediate where the carbon is now sp3 hybridized. Okay, here it was sp2 hybridized, now it becomes sp3 hybridized. So this tetrahedral intermediate is the alkoxide ion, and this is a very common structure that you will see in all the nucleophilic addition reactions of aldehydes and ketones. Okay, in general, aldehydes, sorry, I didn't draw the aldehyde here. So these aldehydes are more reactive than ketones. So in general, aldehydes are more reactive than ketones. The reason being, there are two reasons we can list here. One is the steric effects. Due to the steric effect, so a ketone has two alkyl groups, so they contribute to the steric hindrance in the transition state of the nucleophilic attack. Okay. On the other hand, aldehydes, they have only one alkyl group. So right here it is R, these are the alkyl groups. There is only one alkyl group, so there is less crowding and therefore they are more reactive. Okay. The second reason is described as electronic effect. Electronic effects. And here, if you recall that alkyl groups are electron donating, right? So more alkyl groups means they will stabilize this positive charge more than the one which has got less alkyl groups, right? So when you have a ketone, you have two R groups which are donating electrons, and they stabilize this positive charge on the carbon atom, whereas in case of aldehydes there is only one R group, so they are not so effective as stabilizing the positive charge on the carbon atom. Okay, so you can draw that inductive effect. This is called as the inductive effect. You can draw the arrows here to show the inductive effect. So positive to negative. So this is how they are electron pushing towards the carbon atom here, as a result of which the charge density or the electron density is the positive charge is stabilized in this case. Okay, in case of an aldehyde, you have only a one R group which is donating the electron, so the charge stabilization is lesser as compared to that of ketones. So therefore that makes the aldehydes more reactive. Okay, so these are the two reasons that we list for explaining the more reactivity of aldehydes than ketones. Okay. The general mechanisms of the reactions of aldehydes can be shown under two mediums, one in an acidic medium and the other in a basic medium. Okay, so reactions can generally happen in an acidic medium or basic medium. So we will show a general mechanism for both of them. So for example, if you have a ketone here, okay, the first step in a under conditions of basic medium is, so we can put here, we can describe it here first. Okay, so here under basic conditions, the first step would be where the nucleophile is attacking. Okay, so let's put this as a negatively charged, attacking here at the carbon atom, pushing the electron towards oxygen. You get a tetrahedral intermediate with a negative charge on the oxygen in this manner. And then in the next step, the tetrahedral intermediate is protonated upon treatment with a mild proton source, like in this case I have water here. Okay, so this can grab the proton and we end up in the formation of the final product. Okay, so this is a basic medium. Let's show in acidic medium how the general mechanism can be depicted. Acidic medium. So in an acidic medium, the first step is protonation. So this is my acid. Okay, so if I take any acid represented as Ha, first step is protonation, where the oxygen atom is protonated in this manner, it gets a positive charge. Then in the next step, nucleophilic attack happens. So nucleophilic attack happens in the next step. Electrons are pushed towards oxygen, as a result of which you get a tetrahedral intermediate with a OH. Now that oxygen has lost its charge, this is how you finally get the product. Okay, so the difference, if you see that between the two, in the basic medium, the first step is the nucleophilic attack followed by protonation. Here in acidic medium, the first step is protonation followed by nucleophilic attack. Okay, so here the first step is important because it makes this carbon center more electrophilic in nature. So oxygen, once it gets protonated, it has got more tendency to pull the electron towards itself, making this carbon center a good electrophilic center. Otherwise, if you look at here, in general, the nucleophiles are like water or alcohol. They are not so strong nucleophiles. Therefore, it is important that we make this carbon center more electrophilic in order for the nucleophile to come and attack. Okay. Alright, so now let's look at some specific reactions of aldehydes and ketones with different kinds of nucleophiles. Okay, so let's divide the each of these reactions based on the type of nucleophiles. Okay, so we can write down that the nucleophiles here that are going to attack the carbonyl carbon. Okay, so we can divide them as oxygen nucleophiles. Okay, oxygen nucleophiles. Then we can call the next one as a nitrogen nucleophile. Next one can be a hydrogen atom. Okay, so these are like when I say oxygen nucleophile, nitrogen nucleophile, it means the oxygen atom is the one that is going to behave as a nucleophile. Then here it is the nitrogen, here it is the hydrogen, and the last one is the carbon nucleophiles. So in this first video, let's talk about two of these nucleophiles, the oxygen and the nitrogen. So in the oxygen, under this we will see attack by water, where water molecule is your nucleophile, and here again if you see, oxygen is the atom that is going to do the attack. Another example we can look is alcohol. Under this heading of oxygen nucleophiles, here again oxygen atom is the oxygen is the attacking atom onto the electrophilic carbon center. And then there is one more example that we can look in, and that is it's again alcohol, but it is a diol. Okay, so we have two OH groups attached to the same molecule. So we have a diol. So we'll look at these three examples under oxygen nucleophile. Then under nitrogen, we'll look at two examples. One is the reaction of a primary amine. So if you look at this, is a primary amine where the nitrogen atom is attached to one R group. Or we can also look at another one where the the nitrogen atom is attached to two R groups, and that is a secondary amine. Okay, so we'll look at reactions of primary amines and secondary amines. In case of hydrogen nucleophiles, we will look at lithium aluminum hydride, okay, where again hydrogen is the hydride is acting as the nucleophile, and also sodium borohydride. Okay, so we'll take it as sodium NaBH4. So we'll look at these two examples under hydrogen nucleophile, and under carbon nucleophile we'll look at Grignard's reagent RMGBr. Then another example we'll look at is the cyanide, which is also acting as a nucleophile here, where the carbon atom is the attacking atom. And then the last one is what are called as Wittig reactions, where there are these species which are called as ylids, and we will look at reactions of these. Okay, so we'll talk about these two nucleophiles in another video, but in this particular video, we'll talk about the oxygen and the nitrogen nucleophiles. Okay, all right. So let's put the heading oxygen nucleophile. Oxygen nucleophiles. So first one, we'll look at the reaction with water. Okay, reaction with water. So the overall reaction is, if you represent the overall reaction, when an aldehyde or a ketone reacts with water, you end up, it's a nucleophilic addition reaction, right? You end up with two OH groups attached to that carbon center. Okay, so in general, this is actually an equilibrium reaction. In general, the equilibrium actually favors the reactants than the products, okay, except in simple aldehydes like formaldehyde, but otherwise the equilibrium generally favors the reactant side. Okay, so since the reaction is very slow, we do these reactions in the presence of a catalyst. So we can look at a base catalyzed reaction. That means this reaction can take place either in the presence of a base or an acid. So we'll look at the two mechanisms: base catalyzed reaction. In this, we can see that the first step. So I have taken a simple aldehyde. Remember, this is formaldehyde. The first step is where the base, here in this case, I'm just taking a OH minus, okay, hydroxide. This is functioning as a nucleophile. Put a negative charge. It's going to attack at the carbon atom, pushing the electrons over here. We get the tetrahedral intermediate. Okay, tetrahedral intermediate. And then the next step, remember to put the charge on the oxygen atom. Okay, the next step is where there is a proton source, which is water molecule here. Oxygen gets protonated, and we get the final product, which is this species here. Okay, so this is the base catalyzed mechanism for hydration or for reaction with water. So we call this reaction as hydration because it's reaction with water. Overall, the process is where you have, let me put hydrogens here. Okay, so overall the process is where you get two OH groups on the carbon atom, and the mechanism can be base catalyzed or acid catalyzed. This one we are showing it as base catalyzed. First step is nucleophilic attack. So first step is nucleophilic attack, and the second step is the protonation of the alkoxide. This is the protonation step. Okay, so this is my intermediate tetrahedral intermediate alkoxide, and protonation of that alkoxide results in the formation of this final product. Okay, so this you can use any example. You can use a ketone or another aldehyde. Mechanism will just be the same. Okay, now the next we can also look at if the reaction is acid catalyzed. Okay, So this is a reaction, acid catalyzed reaction. Acid catalyzed reaction. Here the first step, as we discussed in a video, in the a couple of slides, couple of minutes back, we talked about acid catalyzed reaction, where the first step would be protonation, right? So for example, if I take the same aldehyde, okay, which is formaldehyde, okay, the first step will be protonation. Okay, so I can show my acid like this, right? H3O plus. Okay, so this makes the oxygen grab this proton, put these electrons back over here. So my first step is protonation of the oxygen atom. Okay, so this step is important because remember I said that water molecule is a weak nucleophile. So in order for it to attack at this carbon atom, you have to make this carbon atom really electrophilic in nature. And this is accomplished by using an acid catalyzed reaction where this H3O plus, which is your acid in aqueous medium, provides the proton for the oxygen to be protonated. And then in the next step, here we have a hydrogen. The next step is the attack of the nucleophile, which is here water, right? Water is my nucleophile. So the nucleophile adds here. This goes over here. So you end up with a species like this. Now we have the OH, right? So if you follow this, you can see that water molecule attacks here. So this is my water molecule, but since oxygen has 3 bonds, you get a positive charge on the oxygen atom. Now in the next step, another water molecule is going to take away one of the protons here, put these electrons back over here, and that's how we get the final product of the 2 OHs on the carbon atom. Okay, so follow this carefully to see how the reaction happens, and you can see how the product can be formed. So you need to know the mechanism of both base catalyzed and acid catalyzed addition of water to aldehydes or ketones. Okay, so I would like you to now practice the same mechanism by using a ketone now. Okay, so say for example, you take this ketone and do the same reaction, H2O. You can get the product like this. Okay, so write down the mechanism of acid catalyzed reaction, acid catalyzed and base catalyzed. Okay, and base catalyzed. So this will be your assignment to work on this. Okay, all right. Let's do one more reaction here, and that is the reaction with alcohols. Okay, so let's add a new page. Remember, we are still talking about oxygen nucleophiles. Okay, we are still talking about oxygen nucleophiles, and here we are looking at addition of alcohols, and we call this reaction as acetal formation. Okay, acetal formation because the product is actually called as acetal, and this is basically addition of alcohols. Addition of alcohol. So general reaction can be represented like this: plus 2 ROH, which is, we actually need 2 molecules of alcohols. This is again a acid catalyzed reaction, so we can put a H plus here in the presence of acid. It's again also an equilibrium reaction, and you end up with what is called as an acetal. This is what is called as acetal. So you have R groups from here, so the both OR from the alcohol, and this is called as an acetal. Okay. So in acidic conditions, an aldehyde or a ketone will react with 2 molecules of alcohol to form what is called as an acetal. Okay, so when I do this H plus here, this means I'm using a acid catalyzed I'm using acid as a catalyst to complete this reaction. Okay, so let's look at the mechanism. The mechanism is it's a little long process. It's almost like 7 steps. So let's look at it carefully. So the first step would be where since it is an acidic medium, your first step has to be protonation, right? So here I can put H, just to say it's called as an HA, okay, where HA is my acid. Okay, this is my acid catalyzed reaction, so it's the source of protons. So this goes and takes the protons. The first step is protonation. So you get a double bond OH, very similar to what we had seen before, okay, with a positive charge. Pair of electrons here. Okay, the next step would be where the alcohol is acting as a nucleophile and is attacking at the carbon center here, putting these electrons back. So what do we get is a tetrahedral intermediate. Okay, so we get an ROH, just like we saw in the attack with water molecule, right? It's very similar to that. Oxygen gets a positive charge. Okay. Now what's going to happen is this A minus, which was given out in the first step, right? This is going to act as a base, take these protons, put these electrons back here, and what you get is a OH and a OR. Correct? So we have what is called as a hemiacetal because now we have only one OR group attached, but actually an acetal will have 2 OR groups. So what does that mean is we are going to have this whole process repeated a second time. So here again, one more time, we have to react it with the acid. So we get the protonation step first. So proton transfer. So now our structure will look like this. We have an OR already sitting here. We have an O, which has already this hydrogen and this new hydrogen that came up here. So we have a positive charge on the oxygen atom. Okay. The next step would be where this leaves as a water molecule. Okay, so this can be removed as a water molecule. At the same time, now the carbon's valency needs to be fulfilled, so this forms a double bond. Okay, so we get this one here as a double bond OR and minus H2O because we have removed a water molecule from here. Okay, so this is a structure with positive charge on the oxygen atom because it has got 3 bonds. Okay, all right. Now in the next step is where the alcohol is another molecule of alcohol. Remember, we have 2 molecules of alcohols, right? So the next molecule of alcohol is going to attack at this carbon atom, puts these electrons back over here. Okay, so I think I should make it a little more clear. There are only 1 pair of electrons here, right? So this puts the electron back over here, and what we have is a single bond to OR. Oxygen is neutral now here, but then this oxygen gets a positive charge because it has got 3 bonds. Okay, so this is what we have right now. The next step would be where the base is going to grab this proton, push these electrons back over here, and we get our final product, which is my acetal. Okay, I'm just rearranging the groups here, and this is how we get the acetal. Okay, so it's a slightly long process, but I want you to follow the mechanism where take an aldehyde or ketone, react it with alcohol to form acetal in the presence of acid. Okay, so the first step is protonation. Next step, so we can write it here, protonation, first step. Next step is attack of nucleophile, so nucleophilic attack. base removes the proton here so that we get a neutral hemiacetal. The next few steps are kind of a repetition of what we saw before. Protonation again. See, here it is protonation with the acid. Now remember, HA is my acid. Okay, it's my acid. So protonation with the acid, you get this intermediate species. Then water molecule is removed, and here is where you have your nucleophilic attack second time with the alcohol. Formation of this intermediate, base grabs the proton and forms the final product, which is your acetal. Okay. Now this reaction is useful when we use water, when we use the diols. We use these type of reactions in order to protect the aldehyde or the ketone group. Okay, so let me show you that example. So we say that acetals can be used as protecting groups. So if you recall, we had seen in chapter 17 how to protect an alcohol group, right? So here we can do a similar step here where we talk about how we can protect the aldehyde or ketone groups. So acetals as protecting groups. So for that, since it is a reversible process, right, we can take, say for example, if you have a ketone like this, okay, and if you treat it with a diol of this kind, okay, so what you can end up is an acetal of this kind. So this basically what you can do is you are changing a ketone into an acetal, and you can use that as a protecting group. So let me show you an example. So for example, if you had a compound like this where you had a ketone group and you also had an ester group here, okay, and if you treat it with say lithium aluminum hydride. Now remember, lithium aluminum hydrides are powerful reducing agents. Okay, so they are powerful reducing agents. So what would happen is that this lithium aluminum hydride would end up in reducing not only the ketone, but not only the ester, but also the ketone, right? And you will end up with a alcohol group here and a alcohol group here. Okay, so if you want to only reduce the ester and not the ketone, so say for example I wanted to convert this into something like this. Okay, so I want to keep the ketone intact, but I want to change this into a alcohol. Okay, so you think, okay, I can use lithium aluminum hydride, but if I use this, then what will happen? It will reduce the ketone as well as the ester. Okay, so I cannot use this method. So what then I will use is first protect the ketone so that it does not get reduced. Okay, and how can I protect the ketone? That's where I use this diol. Okay, so I'll use this diol first. Again, I have to use the acid. Okay, and what can I get in the first step is this thing. Okay, so I protected that. The ester is left intact, nothing happens to the ester. Now I treat it with lithium aluminum hydride, and you see that the ketone is protected, right? So ketone is protected, so you don't worry about that. Okay, and then you can just end up in the formation of a alcohol at this step. Okay, and remember that esters can convert into primary alcohols. Okay, and once you do that, you can then treat it with, so here we treat with H3O plus, okay, to get the ester, and this will actually take care of this one too. This will also remove this acetal group and convert it back into the ketone. Okay, so it will it's a reversible reaction, so you can get this ketone back and only reducing the ester group. So this is the use of acetal, which can be used as a protecting group. Okay, so again, let's do this one more time, talk about it one more time, that if you have a compound which has got two functional groups, here we have an ester and a ketone, and you need only the ester to be reduced, and if you're trying to use lithium aluminum hydride, then it will end up in reducing both the groups here to an alcohol. Okay, however, if you can take an alternative method where you treat the this compound with the diol, and then protect the ketone with a acetal group, so now the ester is free to get reduced by this lithium aluminum hydride. So you can do this two steps and complete the reaction, where not only it will change it into a primary alcohol, but at the same time it will bring it back to the ketone form. Okay, so keep this in mind of what is the function of making an acetal, okay, or how we can use acetals as protecting groups. Okay, so in the next video we will talk about the nitrogen as the nucleophile. Okay, so I'm going to pause here, and then we can talk about nitrogen nucleophiles in our next video.